Alright, so this is chapter 2, section 2, and what we're going to do is we're going to explore polynomial functions of higher degrees. So, a graph is considered continuous if we have a polynomial function of degree of 2 or higher, and the graphs are smooth and continuous. What do I mean by that? You have to have rounded curves with no sharp corners, no breaks, and it also can be drawn without lifting your pencil from the rectangular coordinate system. I'll show you an example in just a moment. A polynomial function, the continuous portion of this definition means that it's going from negative infinity to positive infinity as far as the domain is concerned. So it's continuous from left to right. Okay, so here's an example of what I mean about smooth and continuous. So if we look over here, I have graphs of polynomial functions. Why? Because they're smooth, meaning if I look here at the corners or where I have maximum and minimum values, I have nice, smooth, rounded corners. Continuous, meaning that it's coming from negative infinity and extending towards positive infinity. And so is this one, smooth and continuous, coming from negative infinity, extending towards positive infinity. But if we look at this one over here, these are not graphs of polynomial functions. I clearly can see a break in the graph right here. And I also see sharp corners here, here, and down here. When we're sketching the graphs of monomial functions, which are the simplest form of a polynomial graph, we're going to have, this should say, to the power of n. Here, let's just change that. So, x to the power of n. If n is even, the graph resembles the graph of our parabola. This should say to the second power, so x to the second power. So just like the graph of the parabola, and here if n is odd, the graph resembles the graph of your cube function. This should say x cubed. Okay. This is an important note. The greater the value of n, the flatter the graph near the origin. So let's take a look at this first example. It says sketch the graph, and let's take a look at the one on the far right. And again, this should say to the fourth power here. So let's just make a note of that. So again, based on what I said previously, this is going to resemble the graph of the parabola. Okay, so let's start evaluating as if it was the graph of the parabola. How did this graph shift? Alexa?
Right one.
Right one. Okay, so the vertex is at 1, 0. Does everyone agree? Okay, what about if x is 0? What's y? Okay. Negative 1 to the fourth power is positive 1. Be careful. And let's pick 2 because we want to go to the left and to the, actually negative 1 because I want to go to the left and to the right of the vertex. If x is negative 1, what happens? Actually, I meant 0. Alright, let's just start graphing that so that way we can see. I'm graphing the point 1, 0. I'm graphing the point 0, 1. Let's go ahead and substitute 2. 2 minus 1 is 1. To the fourth power is 1. So it's creating that shape. The only difference here is that it's been flattened out. And it's creating something that's closer in this direction to the x-axis. So it's kind of like compressed. And that whole section's stretched out. And that's what this higher degree is doing to this graph. In this example, it says sketch the graph for f of x equals x to the 7th power plus 1. Based on what we said a moment ago, this is going to resemble the cube function. If this said x to the 3rd power plus 1, how did that graph move? Up 1, right? So let's take our coordinate plane and move those 3 main points that we know from the cube function. Let's move it up 1. So it's the same points. The only difference here is that it's flatter along here. It should create more of a flattened out look, like that. So it's like kind of squished in at the point where it starts decreasing. Or increasing, I should say, from the left to the right. So let's take a look at this table here. It's our end behavior of polynomial functions. When I have a polynomial function that has a degree that's odd, that the highest degree is odd, meaning the highest exponent I see for the polynomial function is an odd number. The ends of it is going to look like our cube function. If it's greater than 0, it's going to rise on the right and fall on the left. If it's less than 0, meaning our leading coefficient's negative, you're going to rise on the left, you're going to fall on the right. If the highest degree, the highest exponent you see on the polynomial is even, then it's going to look like a parabola on the ends. In the middle, a lot of things could be happening if we have a polynomial function, and we'll discuss that later. But on the ends specifically, if your leading coefficient's positive, then it's going to rise on the right and rise on the left. If it's negative, it's going to fall on the left and fall on the right. So let's go to that and write that. So again, odd degree polynomials have opposite behavior at each end. If A is positive, then the graph falls on the left and rises on the right. If A is negative, then the graph rises left and falls right. If you have an even degree polynomial, it's the same behavior on each end. Think about what's going on with your parabola, because that's what's happening here. They rise together or they fall together. Okay, so let's take a look at this example. Example 2. It says use the leading coefficient test to determine the end behavior of the graph of, and again, that should be an exponent. This should say to the third power here. So we have negative 3x cubed minus 4x plus 7. So what's the highest exponent I see? Third. So the degree is odd. And what is the coefficient in front of that degree? Okay, it's negative. So it's odd and it's negative. So what kind of end behavior happens for this? Good. It rises on the left and falls right. I think it always helps so that when we get to graphing these polynomial functions, if we do a little diagram for us, I know that it's going to follow the cube function, and because it's negative, it's going to have opposite behavior to this pattern. Therefore, it has to go in this direction because it's been reflected over the x-axis. Alright, so we have zeros of a function. Remember, zeros are synonymous with roots, solutions, x-intercepts. So whenever you see any of that, we're referring to the x-intercepts. Okay? So in a polynomial function, the values of x for which f of x equals 0, remember f of x is synonymous with y, are called the zeros of f. Again, roots, solutions of your polynomial equation. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. Notice that we're using the word real root. And this example says find all the zeros of x cubed plus 2x squared minus 4x minus 8 equals 0. So how would I go ahead and find the zeros to that polynomial function? Adrian? I'm going to group the first two terms. What can I factor out? X squared. Good. So I get x plus 2. What can I factor out next?
Factor out 4.
Not just 4, negative 4. Good. And then I get x plus 2. So now that my terms, now that these two are alike, I can group them. So x squared minus 4 times x plus 2 equals 0. And then x squared minus 4, I'm going to go ahead and start solving for that. I got x squared equals 4. X equals plus minus 2. Here I get x equals negative 2. In just a moment, we're going to learn what it means when two roots repeat like this. So therefore, we technically only have two zeros or two roots. That's 2, 0, and negative 2, 0. I don't repeat my solutions, but it does create some kind of behavior when we're graphing.